All right, let's jump right in. Think about the global shipping industry for a second. It's this absolute titan, right? It moves pretty much everything we own across vast oceans. But it has a massive carbon footprint, and the race is on big time to find a clean fuel to power the whole thing. And you know what? The answer might be hiding in a place you'd literally never expect. Yup, you heard that right. We're talking about ammonia. You probably know that pungent smell from cleaning supplies. But could this simple, super common chemical actually be the key to decarbonizing one of the biggest industries on the entire planet? Well, let's find out. So first up, the basics. What exactly are we dealing with here? Ammonia, or NH3, is a really simple molecule. It's just one nitrogen atom bonded to 3 hydrogen atoms. And that shape you see, that trigonal pyramid, that's because of its super strong chemical bonds. And honestly, those bonds are at the very heart of this whole story. Okay, so before we get to all the amazing promise of ammonia, we gotta talk about the problems. Because as it turns out, getting this molecule to actually release its energy is, well, it's surprisingly difficult. This stuff is a very, very stubborn fuel. So, problem number 1 comes from those incredibly strong bonds between the nitrogen and the hydrogen. See, to get energy out of a fuel, you first have to put some energy in to break the molecule apart. And ammonia just holds on tight. It really makes it hard to kickstart that whole combustion process. This is such a great way to think about it. You know, dry paper, it catches fire with just a tiny spark. But wet wood, man, you need a ton of sustained heat just to dry it out before it can even think about burning. Well, that's ammonia. You have to pour in a huge amount of heat just to get the party started. And check this out. This shows you the next problem perfectly. Even when you do get it burning, the flame just spreads at a snail's pace. I mean, look at this comparison. Ammonia's flame crawls along at just 7 centimeters per second. That is 5 times slower than methane. And that's because it's terrible at producing radicals. Those are the tiny, super reactive particles that act like little sparks, jumping from one molecule to the next to keep the fire going. And the challenges just keep on piling up. First, ammonia has a high heat of vaporization. That's a fancy way of saying it sucks up a ton of energy just to turn from a liquid into a gas that's ready to burn. Plus, its nitrogen backbone is, well, it's kind of lazy. Unlike the really energetic carbon atom you find in fossil fuels, nitrogen just doesn't release nearly as much heat when it reacts, which makes it even harder for the fire to keep itself going. So, right about now, you're probably thinking, wow, this sounds like a pretty terrible fuel. I mean, it's stubborn, it's slow, it's unenthusiastic, but there is a huge reason, a massive payoff, that has scientists and engineers working like crazy to solve all these problems. It's the logical question, right? With all this trouble, why even bother? If it's the wet wood of the fuel world, why not just move on and find something else? Well, the answer isn't in how it burns. It's in what happens after it burns. Okay, here it is. This is the big payoff. We're looking at well-to-wake emissions here. That's the total carbon hit from the second the fuel is made to the second it's used in a ship. Now look at the normal fuels. Fuel oil, natural gas, they're all way up there, over 500 grams per kilowatt hour. Now look at the bottom. E-ammonia, that's ammonia made with renewables like wind and solar, it plummets down to around 100. That massive drop isn't just an improvement, it's a total game changer. And here's why that number drops so dramatically. There's no carbon in an ammonia molecule, so there is no CO2 in the exhaust. The funnel of a ship running on clean ammonia would literally just puff out nitrogen, which, makes up 78% of the air we're breathing right now, and water vapor. That's it. No carbon dioxide and way, way less soots and other nasty pollutants. But believe it or not, the clean exhaust isn't ammonia's only superpower. It has this huge practical advantage that puts it way ahead of other clean fuel options. Yeah, even including the much-hyped hydrogen. And here is its secret weapon. We already know how to handle it. See, we've been making, storing, and safely shipping massive amounts of ammonia all over the globe for more than 100 years, mostly for fertilizer. The technology, the ports, the safety rules, it's all there. We don't have to build some brand new global network from scratch. We just need to scale up what we've already got. So this brings us to the core of the whole story. We have this flawed hero, right? A chemical that is both unbelievably promising and unbelievably difficult. The final piece of the puzzle isn't really about the chemical itself anymore. It's about us. So it all boils down to this trade-off. On one side, you have the promise, a clean, zero-carbon fuel that can plug into an infrastructure we already have. But on the other side, you've got the challenge, a stubborn, chemically lazy molecule that just does not want to burn. The whole path forward is about bridging that gap with some really clever engineering. And that's really what it all comes down to. We get the chemical, we know its flaws, and we know its incredible potential. The science is there. So the real question is, can our engineers design the kinds of high-pressure, high-temperature engines and advanced catalysts that we need to finally tame this stubborn hero? Can we solve that engineering puzzle to unlock its clean energy promise? Well, that's the challenge for the future of shipping.